In this video, we are going to review the Chapter 3 exam for college algebra. So this is the first question that you will see on the exam. Find the range of the quadratic function and the maximum or minimum value of the function. Identify the intervals over which the function is increasing or decreasing. So all of these questions can be answered by looking at the vertex and whether the parabola opens up or down. So this function is in standard form. The opening of the parabola is determined by the value of a, which is 2. That's positive, which tells me that the parabola opens up. And the vertex we have to calculate because it's in standard form by using the formula x equals negative b over 2a. So while the directions don't specifically ask you to find the vertex, you need to know the vertex in order to answer the questions you are being asked, right? B in this case is 5. So we're going to have, this is going to be a bad one here. 5 on top, right? We have the negative sign from the formula. B is 5 over 2 times A, which is 2, which is going to give me a value of x of negative 5/4. This is the bad one because that's a fraction. We have to plug that in to the function in order to find the y-coordinate of the vertex. And this is where things get kind of messy. So we get 2 times negative 5/4 squared plus 5 times 5/4 plus 5. Simplify. Now, if you have a calculator, maybe this is just an easy step for you, but I'm going to work this out by hand. So we square the top. So negative 5 squared comes out positive 25. Square the bottom. 4 squared gives me 16. Plus, here I'll multiply these together. 5 times 5 gives me 25 on top. 1 times 4 gives me 4 on the bottom. Plus, here we're going to have 5, which is going to have to interact with these fractions. So let's think of that as 5 over 1. Continuing on, here the 2 cancels out with the 16 and leaves me with an 8. And so I'm going to have to get a common denominator. 8, 4, and 1, the common denominator is going to be 8. So this fraction can actually just stay as it is. This one, however, we have to make this an 8 by multiplying a 2 to the top and bottom, so we get 50 over 8. And this one we'll make an 8 by multiplying an 8 to the top and bottom, and we get 40 over 8, which allows us to combine these together into a pretty big number. I have to say, this is maybe one of the more extreme examples I've seen from this exam. The common denominator is 8, but we're going to get 90 plus 25, that's 115, right? Which I don't think this reduces. So that's it. The y value is 115 over 8, right? And so that's the y coordinate for the vertex. Actually, all of this stuff we can find by sketching a really rough draft of this graph. I don't know if that's the right way to say that, but a rough sketch, right? It doesn't have to be perfect. We don't need to get the intercepts. We don't have to look for symmetry. We don't have to do any of that extra stuff. Just with the vertex and the opening, sketch a graph of this parabola, right? And so it's going to look like this, right? So negative 5/4, I don't even have to get this number exactly right. All that really matters really is that it's negative. So it's going to be over here, right? Negative 5/4 will be over here. And then the y-coordinate is positive 115 over 8. So it's going to be up here somewhere. Don't worry about the scaling. And then from there, it's going to open up. Wow, this one's just really odd. I feel like they normally don't behave in this way. But this picture tells us exactly what we need to answer all these questions. The range is how far down the graph goes, how far up, right? So the range in this case, how far down, the lowest point is this point here. The y-coordinate for that point is 115 over 8. How far up? Infinity. Right, so that's the range. That answers the first question. It tells us it's a minimum, but sometimes on these questions it'll ask you that. Is it a minimum or a maximum? The directions even kind of ask that, but then the answer, they already made that decision for you. It's a minimum. But if it opens up, the vertex is a minimum. If it opens down, the vertex is a maximum. So we have a minimum value at y equals 115 over 8. Right, that is the lowest y value in this graph, right? That's as low as it's going to go. And so whatever that number is from the range, that's going to be your answer for the minimum or the maximum as well, whatever that number is. One will be infinity or negative infinity. The other one will be a number. That number is the answer for the minimum or maximum value. Where is it increasing? So we want to answer that one first. So remember from chapter 2, you have to look from left to right. So you have to start over here. And as we look to the right, this part of the graph is decreasing. It's dropping as we head to the right. And then once it hits the vertex, then it starts ticking back up. And so it's increasing on the right half of the parabola. So here's where it's increasing, starting at, and you have to use the x-coordinates here, starting at negative 5 over 4, forever to the right, to infinity, is where it's increasing. All right, so that's the increasing part. It's decreasing from negative infinity, right, on this side, starting from the very left-hand side, negative infinity, up until x equals negative 5 over 4. So you want to use the x-coordinates to describe the increasing and decreasing. You use the y-coordinate to describe the range and the minimum or maximum value. Right. So you needed both parts of the vertex to answer these questions. Right, I'm sorry, that didn't look right here. So decreasing. Okay. So a lot going on in that problem. Sorry it took me 7 minutes to get through that first problem. Let's go on to the next one. Some of these won't be quite as lengthy as that particular problem was. Let's zoom in on these. All right. But some of these are lengthy, and I apologize. That's just, I shouldn't apologize. It's not my fault. That's just the nature of these problems. They're just long, tedious problems. All right. So this is another quadratic function, just like question number 1, but this time it's in vertex form. So the formula you want to match that to is this formula here. All right. And the reason you want to match it to that is it will help us with the opening of the parabola, but also for identifying the vertex. So when it's in vertex form, the vertex is just at h comma k. Remember, h will be the opposite sign of this number that's being added or subtracted to x. This is a plus 3, so k is negative 3. That plus 3 actually shifts the graph to the left 3, and so the vertex will be at negative 3. K keeps the sign of that number, so plus 8 means k is positive 8, and so my vertex is at negative 3 comma 8. I can go ahead and plot that point. Now that's the vertex. The next part is the axis of symmetry, which is super duper easy. Now on Canvas, you won't be given these two options. You just need to know how to describe the axis of symmetry. But it's just whatever the x-coordinate of the vertex is, it's just x equals that number. That's the axis of symmetry. It's always x equals whatever. So here they give you the option of x equals or y equals, and sometimes I'll get students picking y equals, but it's never that one. The axis of symmetry is always x equals the x-coordinate of the vertex. And it's this vertical line, right? So it's not even just a number we're talking about. The axis of symmetry is a line that passes through the vertex. It's a vertical line. And so we describe that vertical line as x equals whatever the x-coordinate is on that vertical line, right? Every point on this vertical line, I kind of missed the mark there. I'm a little bit off of where it's supposed to be, but it's every x-coordinate here is negative 3, which is why the equation is just x equals negative 3. It's the line where every x-coordinate is negative 3. That's that axis of symmetry. The y-intercept, it's not 8. That's a common mistake students will make. You actually have to calculate it. It's not, you can't just read it off the equation this time, right? To calculate the y-intercept, you plug in 0 for x. So we're going to get 0 plus 3 squared plus 8. And then you're going to simplify. So we get negative 2 times 3 squared plus 8. That's going to be negative 2 times 9 plus 8. Which is going to be, I don't know how much more detail I want to put here. I guess I'll just continue to put all the detail. Negative 2 times 9 is negative 18. Negative 18 plus 8 is negative 10. We get that. Now we plugged in 0 for x. We got y equals negative 10. So that gives me the point 0 comma negative 10. And so I have another point. X-intercepts. Right, so to calculate these, it's going to take some work. So let me take advantage of the fact that I can scroll from side to side here, and we'll just put the x-intercepts over here. Now to find the x-intercepts, you set y equal to 0, so we're going to plug that into the equation. We get 0 equals negative 2 times x plus 3 squared plus 8, We'll solve this for x by subtracting 8 from both sides first. All right, there's other ways you could go about solving this, but this is by far the easiest path to take. Just get x by itself. Subtract 8, divide by -2 to cancel out the multiplying by -2. We get 4 equals x plus 3 squared. Then we will take the square root of both sides to cancel out that power of 2. But when you do that, be careful. You have to do plus or minus. So plus or minus square root of 4, which is 2, equals x plus 3 because the square root cancels out that power of 2. And then you subtract 3 from both sides. And usually you put that in front of the plus or minus, but it doesn't technically matter, mathematically speaking. So you get -3 plus or minus 2 equals x. And then we don't want to leave it as plus or minus because we want to know what those numbers are actually equal to. So we're going to consider both answers individually, one using the plus sign, one using the minus sign, and we get x can equal -1 and x can equal -5. And so those are my x-intercepts. So again, y was equal to 0, so this is going to be -1, 0 and -5, 0 for both of these. Okay. So now we have a couple more points to plot, which I'm going to do in just a second. But while we're down here, let's talk about this last one here, the opening of the parabola. So a is -2 in this problem. That's negative. And so this parabola will open down, right, which we can already see happening with the points that we have. So we have -1 and -5. So -1 is right here and -5 is right here. Now the symmetry gets me another point for free because for this y-intercept, it has to have a mirror image symmetric point the same distance away on the other side of the axis of symmetry. So this is 3 to the right of the axis of symmetry. And again, my line is a little bit off the mark here. So try not to go by that too much because I drew it really badly. 3 to the left would be at -6. I should have another point located there. So I think it'd be right here. So that's at -6, comma -10. And with those 5 points, the parabola is unmistakable, right? It's right there. I can see it. I can visualize it, but I don't know if I can draw it very well. So, okay, so there is the graph. All right, let's move on to the next problem. It's a word problem. So far, these problems have been pretty lengthy problems. That's okay. There's going to be some shorter ones eventually. If an archer shoots an arrow straight upward with an initial velocity of 128 feet per second from a height of 8 feet, then its height above the ground in feet at time t in seconds is given by the function h of t equals -16t squared plus 128t plus 8. So you can tell I've read this question many, many, many times. And so notice the 128 goes here, the 8 goes here. So those are elements of the scenario that get plugged into this formula, but they go ahead and set it up for you. They could have just given you the formula and made you plug those numbers in. But what's the same every time is this number, -16, and that number is there because of gravity. This is working to push the arrow back down to the ground. These work to put the arrow further up into the air, and so that's the interaction there. You have the person shooting the arrow, gravity working to slow the arrow down and eventually cause it to fall back down to the ground. What is the maximum height reached by the arrow? So as soon as you see the word maximum or minimum, and it's a quadratic function like this one is, you should think vertex. That maximum or minimum will occur at the vertex. This is in standard form, so again, to find the vertex, just like we did on the first question, we have to do -b over 2a. b in this case is 128. A is -16. This time we're going to get a more respectable, maybe respectable is not the right word, but a nicer answer. I feel like there's a better word than that I could have used. We're going to get 4. All right. Now I'm putting x here because that's the x coordinate of the vertex, but the x variable in this problem actually isn't called x, it's called t. And so sometimes students will mistakenly think, oh, the maximum height is 4, but that's not the height. That's the time. In fact, that's the time it takes for the arrow to reach its maximum height. All right, so this is going to take 4 seconds. After we hit the 4-second mark, the arrow has reached the highest height it's going to reach. But that's not what we're looking for. We don't want to know how long it takes to reach the maximum height. We want to know what is that maximum height. And so to find the height itself, we have to take this value of x, plug it into the equation to find h. So it's the y-coordinate that gives us the height that we're looking for. We have the x-coordinate. We need to find the y-coordinate. All right, so let's go ahead and do that. We're going to have h of 4 equals negative 16 times 4 squared plus 128 times 4 plus 8. Right. And so we'll just work this out by hand again. 4 squared is 16. This is going to be 256. But then we're going to have that plus 8 there. So ultimately we get 264. Right. So the maximum height is 264. That's part A. Right. All this stuff is for part A. Okay. I think that covers that. I was trying to think. It felt like there was something else I should say there, but I can't think of what it is. Part B is, how long does it take for the arrow to reach the ground? The height, when the arrow has reached the ground, it has a height of 0. Right? So it doesn't tell you h is equal to 0. You have to infer that from the description. But when the arrow hits the ground, its height above the ground is 0 feet. It's on the ground itself. It has no height above the ground because the height is 0. And so you want to plug that into the equation. Right? So we have h of, why am I putting 4 here? H of t equals negative 16 t squared plus 128 t plus 8. And we want to find when the height is 0. What's the time that it takes for the height to be 0? So we plug in 0 for h, and we get this unfortunate quadratic equation to solve. Unfortunate because it's not, it is factorable. I was catching myself there. We can factor out an 8, maybe? I don't know. Let's see. I just brag about being familiar with these numbers, and now I'm not sure. Yeah, we can factor out an 8, which would make the numbers a lot smaller, but you can't solve it by factoring. We're going to have to use the quadratic formula, right? And so that's unfortunate, right? But we can make it. Now, usually I don't do this. Usually I just leave the numbers as is, but why not? Let's make these numbers smaller, so when we plug it into the quadratic formula, it's that much easier to deal with. Factor out an 8. Factor out a negative 8. Let's just factor out a negative 8. That gives me 2 squared plus, not plus, minus 16. And I said 2 squared. I'm sorry. 2t squared minus 16t plus 8. Plus 8. Oh man, I'm making so many mistakes right now. And it's not plus, it's minus. Oh gosh, okay. Maybe I should take a break. All right. Factoring out a negative 8. Make sure you factor it out from every term. Learn from my mistake, right? 8 should be coming out of every term. And also, since I'm factoring out a negative, which is really a good choice if you don't make a mistake when you do that, it changes the sign of these terms, right? So this is what we should end up getting when you factor out negative 8. And then that can just be discarded because as far as solving the equation, this is not going to contribute anything. It's this thing that we need in order to solve the equation. So a is equal to 2, b is equal to negative 16, c is equal to negative 1. Right, you see, like when I go off script, how I'm vulnerable to making mistakes, right? Because like I said, I normally don't do this. I usually just leave the numbers as is and jump right into the quadratic formula. But I tried something different this time and it got me in trouble. All right, so the quadratic formula, remember, is negative b plus or minus the square root of b squared minus 4ac over 2a. And there's our values for a, b, and c, so let's plug those in. We get negative of negative 16 plus or minus the square root of negative 16 squared minus 4 times a, which is 2, times c, which is negative 1. I don't know what's wrong with me today. I feel like I'm saying things before I think about what I'm saying, and then I'm thinking about it after I say it. So that's kind of why I'm sitting there pausing like, okay, did I just say what I meant to say? And is it the right thing to say? I don't know why I'm doing that to myself. Over 2 times a, which is 2. Okay, so 16 squared, all right, is 256. after I just bragged about knowing these numbers really well. I had to use a calculator for that. Now, negative 4 times 2 times negative 1 is going to be positive 8. Right? So this breaks down to positive 16, right? Because negative of negative 16 would be positive 16. Plus or minus the square root of these added together, that's 264, right? Over 2 times 2, which is 4. All right. I think that's really weird. I don't know if that always happens. I guess it doesn't normally because I normally don't factor out the 8. But it's so strange to me that we got 264 and that was the answer over here as well. And that's what we're getting in the square root here. So I'm wondering, does that always happen if you factor out the common factor? I don't know because I don't normally do that. So take the square root of 264 and I get 16.24. It's a decimal. All right. So we're going to have t equals 16 plus or minus 16 again. Sorry, I was skipping to the decimal part. 16.248. I'm just going to stop there. 1 over 4. Now there's 2 answers here, but one of them will be reasonable and the other one will not be reasonable. So, but we should consider both of them. So we'll have 16 plus 16.2481 over 4, right? That's one answer using the plus sign. And then we'll have another answer using the minus sign. But you see, when you use the minus sign in this case, this number will come out negative. It'll be negative. I was about to use my calculator, but I don't need it. Negative 0.2481 over 4. And the answer is going to be negative, which just does not make sense. You can't have a negative amount of time for the arrow to reach the ground. So this answer doesn't produce anything sensible. So the correct answer must be this one. So I'm going to take that 16.24 whatever, add 16 to that, divide by 4, and we're going to get 8.06 seconds. And I think 2 decimal places is enough. So that's how long it will take for the arrow to fall back down to the ground. And it makes sense because if you think about what's happening in the graph, it's going to look something like this, right? And so the arrow's starting at 8 feet. Now this is actually quite short. It should go way up higher than this, but point still stands. It takes, we found, 4 seconds to reach the maximum height. So here's the maximum height. It takes 4 seconds to reach the maximum height. It'll take another 4 seconds to get back down to 8 feet again, right? So this will be another 4 seconds, which will be 8 seconds. Then it's going to take an additional fraction of a second to fall the rest of that 8 feet, right? Because we're not asking how long does it take to get back to where it started, which is at 8 feet. We want to know how long it takes to get back down to the ground. So it has to cover that extra 8 feet distance on the other end, right? And that's why it's a little more than 8 seconds, right? So 4 seconds to reach the maximum height, another 4 seconds to get back to the original starting height, and then a little bit more to fall the rest of the way to the ground. Okay, let's take a look at another example on the test. All right, number 4. So these are going to go a little bit more quickly, I think. So here we have x minus 3. We want to know if that's a factor of this polynomial. The way you're supposed to check is to divide. And the way you want to divide is to use synthetic division. So you're going to set up synthetic division. The value of c is this number here, except opposite sign. So c is going to be positive 3. The coefficients of this polynomial go across the top inside the box. So we have 1, 5, negative 12, negative 36. We run through the process of synthetic division. Drop the 1. 1 times 3 is 3. Add those together, you get 8. 8 times 3 is 24. Add those together, you get 12. 12 times 3 is 36. Add these together, you get 0, which is exactly what you want to see for it to be a factor. So if the remainder is 0, the answer is yes. It's a factor. If the remainder is not 0, the answer is no. It's as simple as that. Either it's 0 or it's not. If it is 0, it's a factor. If it's not 0, it's not a factor. Unfortunately, for this problem, if it is a factor, then you have some more work to do. If it's a factor, then go ahead and factor this polynomial. So I want to factor this. Now, this divisor, which is not just 3. A lot of students say, oh, I divided by 3. You didn't divide by 3. You divided by x minus 3. That's one of your factors. So this polynomial here will factor as x minus 3. That's one of the factors. The other factor is this quotient here, which is x squared plus 8x plus 12. Right? And so I factor it. I factor this polynomial using my divisor and my quotient. And I can do that only if the remainder is 0. And once you factor it down to this, you can factor it some more. Because this is now quadratic, I can factor it further by using the old techniques that we're familiar with, which is, for this situation, what two numbers multiply to 12 and add to 8? Those two numbers will be, now I'm going to copy the x minus 3 over, but those two numbers are 6 and 2, right? 6 and 2 multiply to 12, but add to 8. And so that's how this part factors, right? And now that's completely factored. And it says, factor the polynomial completely. So some students just stop here. And that is factored, but it's not factored completely. So you want to initially factor it using your divisor and your quotient, and then take the quotient and factor it down even further. But at this point, you don't need synthetic division to help you figure it out. We have methods that we've learned previously for factoring quadratic things like this. And so use those old methods to factor it the rest of the way. All right, number 5 is even quicker. We want to know if this number is a 0 of this polynomial. Now, one way you could check is just to plug it in. Plug it into that polynomial and see if it makes it equal 0. But that's actually the longer way to go about it. The fastest way to go about it is to use synthetic division again, because if the remainder is 0, then that number makes the polynomial equal 0 when you plug it in. And so then we would answer yes. If the remainder is not 0, we answer no. So again, it's just a simple, either it is or it isn't. Either the remainder is 0 and the answer is yes, or the remainder is not 0 and the answer is no. So this time, this is what confuses students. For the synthetic division, you keep this number as is. Because if they give it to you as a factor, you have to switch the sign of that number to get the value of c. But if they just give you the number itself directly, that is the value for c. Use it as is. So we're going to use -3. Here we'll have 3, 8, -7, and -13. Let's run through the same process again. Drop the 3 below the box. 3 times -3 is, I was about to put 27. Oh, what's wrong with me? -9. Add these together, you get -1. Multiply, you get 3. Add these together, you get -4. Multiply, you get 12. So close, right? Oh, I was about to put 0. I guess that's what I wanted to see, but that's not what we get. Right? We get -1. And so the answer is no. -3 is not a 0. It also means that x plus 3 is not a factor of this polynomial. The answer is no. Now 6 is another lengthy problem that we have to do on the test. Find all of the real and imaginary zeros of the polynomial function. They don't give us any numbers to try. We're on our own to come up with our own set of guesses, and then we're going to check those guesses by doing synthetic division. To save time on the recording, I'm going to go ahead and we'll develop our list together, but then I'm going to off screen start checking them until we find one that works, and then I'll resume when I find one that actually works, so that you don't have to sit there and watch me make all these bad guesses. All right, so to develop our list of guesses, we have to look for values of p, which come from the constant term, and values of q, which come from the leading coefficient. They have to be factors of these numbers. So p has to be a factor of 18, which the factors of 18 are 1, 2, 3, 4 doesn't work, 5 doesn't work, 6, 9, and 18. Right? And the reason I kind of skipped ahead there is once you get a pairing like this, 3 times 6 is 18, the rest of the numbers have to be pairs with the initial set of numbers. So once I find that first pair, I just go back to 2 and I say, well, what do I multiply to 2 to get 18? You multiply by 9, so 2 and 9. And then 1. What do I multiply to 1 to get 18? 18. And so the rest of them just have to pair off like that. For Q, I'll write it down here, I guess, has to be a factor of 54. 1 always works. It's even, so 2 works. It can be divided by 3. 4 does not work. 5 doesn't work. 6 works. But again, 3 and 6 are not pairs, right? Because 3 times 6 is not 54. So I'm still looking for my initial set of numbers. 7 doesn't work. 8 doesn't work. 9 works. Now 6 times 9 does give you 54. So that's my first pairing. From there, the rest of these numbers have to pair with the initial set of numbers. So now it's just a matter of, well, what do I multiply to 3 to get 54? Because that's going to be the next number in my list. And it's one you probably wouldn't normally think of for 54. And you can find out by doing a division in your calculator. 54 divided by 3 gives me 18. So the next number in my list is 18. I can skip 10, 11, 12. None of those can work. 18 is the next number in the list. For 2, it's going to be 27, because 27 times 2 give me 54. And for 1, it's 54. And so that gives me my list of values of Q. We have to take every possible combination of a P divided by a Q. So I'll start with Q equals 1. 1 divided by 1 is 1. 2 divided by 1 is 2. 3 divided by 1 is 3. So you get the idea. 6, 9, 18. That takes care of Q equals 1. Then we do Q equals 2. 1 divided by 2 is 1/2. 2 divided by 2 is 1, already on my list. 3 divided by 2 is 3/2. 6 divided by 2 is 3, already on my list. 9 divided by 2, that's a new one. You almost thought we were done, right? But nope, there's that extra one there. And then 18 divided by 2 is 9, already on my list. That takes care of Q equals 2. So why don't I just pause the recording for this as well. Finish finding the rest of the possible zeros that need to go on this list. We're already up to Q equals 2, so the next one's Q equals 3. Go through all the values of P, then do 6, then 9, then 18. And then resume the video to check and see if you got all the same numbers that I got. So I'm going to pause it, and then you should do the same. See if you can figure out what the rest of them should be. All right, so here are the rest of the numbers that I came up with for this list. 1/6, 1/9, 2/9, 1/18, 1/27, 2/27, and 1/54. Any other combination just reduces to something that's already on the list. I'm pretty sure I thought through all of those correctly. So now, these are the only numbers that could possibly be zeros to this polynomial that aren't imaginary and that aren't radicals. And those we can't even find by synthetic division anyway. So these are the only zeros that we will be able to find via synthetic division. And if it's not on this list, it can't possibly work. So I'm going to start checking these. I have no idea which one or ones can work on this polynomial. I have a feeling they might be fractions. I don't know. Maybe some of these whole numbers work. You're going to have to start checking them by synthetic division, and you want to do that quickly and methodically and correctly so that you can make sure to find one that works. So it's a good chance to practice it yourself. Now, you might find a number that works, and I might find a different number that works. And it doesn't mean that you're wrong. It just means we just found two different numbers, and they both work, but we just happen to find different ones. But eventually, we will come up with the same set of numbers. So once I break things down, factor it, solve it, I'll have the same set of numbers that you would have. So even if our first number that we find might be different, so from each other, I'll eventually find the one that you found, and you'll eventually find the one that I found. Okay, so I'm pausing the recording, you pause the video, start checking these numbers using synthetic division, see if you can find one that gives you a remainder of 0. That's what we're looking for. Okay, well, I was extremely lucky. The first number I picked happened to give me a remainder of 0, so that's why you don't see other work. I wouldn't have erased it. My plan was I'll get a couple of these wrong, I'll leave them on the screen so you can kind of see how that looks, and then I find one that works that gives me a remainder of 0, but it happened to be the very first number I picked worked out, so I ended up getting to a result pretty quickly here. So once you find a number that produces a remainder of 0, you can stop and factor this polynomial, just like we saw with question number 4. If the remainder is 0, you can factor the polynomial. And these are going to be a little bit strange looking factors, but your factor, the thing you're dividing by, your divisor, is x minus this number here. Right? And that's going to be one of your factors, and it's a fraction, so it's x minus 2/3, but that's the fraction, that's the factor you get from that 0, right? This is a 0, that's going to be a factor. The other factor will be your quotient. So you're going to have 54x squared minus 99x plus 27. And now that you have one factor down to a quadratic level, you don't need to do any more synthetic division. You can get the rest of your zeros from that quadratic expression, either by using the quadratic formula or hopefully by factoring this polynomial. By factoring out the common factor, so let's see if I can do that right this time. So we factor out a 9, we get 6x squared minus 11x plus 3. So that really brings these numbers down to earth where they're a little bit easier to work with. AC method would be a good path to go, but it takes a little time. So I'm just going to kind of guess at what I think this is going to look like as a factor. I'm thinking 3x and 2x. Now I'm guessing the factors, but I will have to confirm my guess is correct. So I'm not just making something up here and saying, let's just pretend this is right. I'm making a guess. I'm going to confirm that it's actually how it should factor. And then once we've confirmed it, then we can use it to get our answers, right? So 6x squared, we can get that from 3x and 2x. We could also get that from 6x and 1x. And so you have to remember that's another possibility. To get 3, it's going to be 3 times 1, but I have to decide where the 3 goes, where the 1 goes. 3 can't go here because then you get this common factor of 3, which isn't present in the problem, right? We factored out the 9. There's not a common factor of 3 left. So your answer can't have a common factor of 3 left. So the 1 would have to go here, the 3 would have to go here. Now, I can't just assume that this is automatically the way it factors. I need to check. Now, the other thing is I want this to be a positive 3 when I multiply these together, but I want the middle term to add up to a negative result, so these need to both be negative for that to happen. And then I check my guess by foiling. So first, and I'm just going to do this mentally, 6x times 2x, sorry, I said the answer. 3x times 2x gives me 6x squared. 3x times negative 3 is negative 9x. So try to hold that in your memory for a second, right? Negative 9x. The inner terms give me negative 2x when I multiply them together. Negative 9x minus 2x is negative 11x when you combine those together. And then negative 1 times negative 3 is positive 3. So that is indeed how it factors. So now that we have these two factors, we can get the rest of our zeros. All you have to do is set them equal to 0. So we'll get 3x minus 1 equals 0, and we will get 2x minus 3 equals 0. Solve for x in each case. And so I'm going to add 1 to both sides here. We get 3x equals 1. Divide by 3 on both sides. And I'm just going to write the answer up here. We get x equals 1/3. Right. Here we add 3 to both sides because I'm already like taking up the space of other problems. I should have been more careful about how I planned that out. Add 3 to both sides, divide by 2, you get 3/2, right? That's your other answer from that. And then your original answer for me was 2/3. Now again, if you actually paused the video and tried to find zeros on your own, maybe you would have found 1/3 first, and you might have had 1/3 here. And then these details would look different. But if you found 1/3 first from your synthetic division, then from your factors, you would get 3/2 and 2/3. You'd get the other two. So this one, state the degree of the polynomial. Remember, the degree is the highest power of x, which in this case is 5. So that's degree 5. That's an easy 1 point on the test. Then find all the real and imaginary roots to this equation, which is like finding zeros. But this time we don't have to do p's and q's because this can be solved by factoring. So factor out the common factor, which is x to the 3rd power. And that's going to leave me with x squared minus 4. I'm not done factoring, right? X squared minus 4 can be factored even further. This is going to factor as x plus 2 times x minus 2. Right, that's how that one factors. And then we set each factor equal to 0. And we do indeed get 0 as one of our roots. This is going to give me negative 2 as a root. Right? Set it equal to 0, solve for x, you get negative 2. This factor gives me positive 2 as a root. So multiplicity, this x equals 0, occurs 3 times. Right? The exponent's 3. That means we're getting this answer 3 times. So the multiplicity of that root is 3. These answers, the exponents are 1, so we're only getting these answers once each. And so these each will have a multiplicity of 1. All right. So to fill the rest of this in, 0 is a root of multiplicity 3, because we get that answer 3 times. And the two roots with multiplicity 1 are negative 2 and positive 2. Find a polynomial equation with real coefficients that has the given roots. 8 and 9 minus I. So remember, the 9 and the minus I are together. A lot of students will separate them and put 9 in one place and negative I in another place, but it's one number. It's one root. You can't split it up like that. So if we want 8 to be a root to our polynomial equation, that means 8 will be a 0 to our polynomial. And if 8 is going to be a 0, then x minus 8 would have to be a factor of our polynomial. So that's how we're going to work backwards from the solution to the equation. Right? We take the solution, and I don't know how we want to say this. Whatever the solution is, we take x minus that solution to make it a factor of the equation. It's the exact reverse of what we just did here, right? Because x plus 2 was a factor, we knew negative 2 was a 0. We're just doing that in reverse. If negative 2 is a 0, that means x plus 2 had to be a factor to give me that 0. So the same is true for 8. If 8 is a 0 of our polynomial, then x minus 8 would have had to been a factor in order to get that 0 of 8. And the same pattern holds true even for this complex number. If 9 minus I is a root or a 0, then x minus that number would have to be a factor. So following the same pattern, x minus whatever that number is must be a factor of our polynomial. Now, if we stop there and this is all we work with, then we're going to get a horrible looking polynomial. It'll have ix, it'll have 8i. It doesn't look like the polynomials we've been working with throughout this entire chapter, because we'll have imaginary numbers in the polynomial. And while it's okay to have imaginary solutions to a polynomial, we really don't want imaginary numbers in the polynomial itself. I don't want a polynomial with ix or 8i as part of the expression. And we don't want that here either. You might say, well, why can't I just have that as my answer here? Because the directions here forbid it. The directions say the polynomial should only have real coefficients. You can't have imaginary coefficients in the answer. And so in order to avoid those imaginary coefficients, we have to know that if 9 minus I is a root to my equation, then 9 plus I would also have to be a root. Right? So we have to add the conjugate to this list of roots in order to get a polynomial of the type that we want. Right? That adds another factor to our polynomial. So we're going to have x minus 9 plus I added to our factors. So what we're going to do to multiply these out is start with the imaginary ones first. So we're going to FOIL there's a couple of ways you can work through this problem, but the way I like to think of it is just simple FOIL. At least it's simple with this, how do you say this? It starts off simple, right? My approach is a simple approach to start working on this problem. There's a more complicated approach which makes the work simpler, so it's sort of a matter of, do you want it to be simple at the beginning or simple at the end, right? I'm going for simple at the beginning. Let's just FOIL it, right? It's 2 terms times 2 terms. Just do FOIL, F-O-I-L, right? I don't know what color to use here. Let's go with green. So first, outer, inner, last, right? Now, x times x gives me x squared. X times this thing here, it's positive times a negative, which is negative. And then we'll have x times that parentheses, 9 plus I. Then the inner terms, it's negative times a positive, which again is negative. We have x, which we'll put first, times 9 minus I. And again, I could have taken as much space over here as I wanted, and I cut myself short here. So this is, this is frustrating. Why did I do this to myself? The last terms, negative times a negative is positive, and then I'm going to have to run into this space over here. 9 minus I times 9 plus I. Distribute the negative x, and then FOIL. We're going to have to FOIL this again. So we're going to have to do FOIL again on this. And I'm going to try to plan a little bit better this time and move this out a little bit further to the left. So we'll have x squared. We'll have negative 9x, and then negative ix when I distribute this negative x into that parentheses. Here we get negative 9x plus ix when I distribute the negative x here. Negative times a negative makes that positive ix. And then here we FOIL, we get 9 times 9, which is 81. 9 times I, which is 9i. I'm still going to run out of space. Negative 9 times I, which is negative 9I, and then negative I times I, which is negative I squared. All right. Now it gets really bad here. Now, and you might say, well, maybe we should have went with the more complicated approach that had a simpler ending. And yeah, it would have been less complicated than what we have here now. So now things, even though it got pretty complicated here, things are about to simplify dramatically, right? Negative ix and positive ix cancel each other out. Plus 9i, negative 9i cancel each other out. I squared becomes negative 1, so we get minus negative 1, which becomes plus 1. And we can combine all these things together that are left, so we get x squared minus 18x when I combine these together, and then 81 plus 1, which gives me 82. So it really comes out quite nice once you get past that part right there. Now we still have one more thing to deal with here, which is the x minus 8. So we have to multiply these together, but this part's not nearly as challenging. It's not FOIL. You have to multiply every term here to every term here. So it's like distributing. So the x gets multiplied to each of these. So we'll get x to the third power minus 18x squared plus 82x. And then we'll distribute the negative 8 here. I'm going to have to use my calculator for some of these. So we get negative 8x squared. 8 times 18 is 144. It'll be positive because it's negative times a negative. And then negative 8 times 82 will be negative, what am I doing? 8 times 82, 656. And it'll be negative, right? Because negative times a positive. Lastly, we will combine like terms again. So we have x to the third power. These combine together to give me minus 26x squared. These two combine together to give me 144 plus 82, which is 226. X minus 656. And we set it equal to 0 to make it an equation. And we're finally done with that problem. So that was kind of a lengthy one as well. All right, let's take a look at number 9, the last one on the page. And I guess we'll try to put the work in this space right here that we have available. So we have x to the fourth power minus 4x to the third power plus 28x squared minus 100x plus 75 equals 0. We want to find the roots of this equation, which are, how am I going to say this? We want to find the roots of this equation, which is going to require us to do the p's and q's again and do synthetic division again. So there's 2 problems on this test where you have to do p's and q's and synthetic division to find the zeros. We skipped Descartes' rule of signs. We skipped theorem on bounds. You don't need those to do this problem. So we're going to do this problem the same way we did the previous one, number 6, right? So P has to be a factor of the constant term, which is 75. What are the factors of 75? Well, 1, 3, 5. What works after this? I guess 15. Like 6, 7, 8, 9, 10. I don't think any of those work, so I think it's just going to be 15, 25, and 75. Pretty sure that's it. Now, what's nice about this problem is Q is a factor of the leading coefficient, and that's just a 1. So that's all Q can equal. Then we take every possible combination of a P divided by a Q. That's going to be 1 divided by 1, which is 1, 3 divided by 1, which is 3, so on and so forth. You get 5. 15, 25, 75, and it can be positive or negative. Right? So plus or minus any of those. Now I'm going to give you a big hint here, which I think on Canvas, I typed this hint in there. So even if you don't watch this video, you'll still get this hint on the test. But 1 always seems to work on this particular problem. And I only really give that hint because this one wasn't so bad. 75 was not that difficult to work with. But sometimes the numbers they put here are ridiculous. You'll get like 534 or something like that. And then trying to find all those factors can be challenging, maybe even discouraging to the point of like just wanting to skip it. So just remember, if you don't want to make this entire list of P's and Q's, you can actually get by without it with the hint I'm giving you, which is 1 should work. So let's just go with 1. I'm not going to pause the recording because I'm pretty sure 1 is going to work here. So we have 1 -4, 28, -100, and 75. Right, those are the coefficients of our polynomial. We do the synthetic division. I'll drop the 1 below the box. 1 times 1 is 1. Add those together, you get -3. -3 times 1 is -3. Add those together, you get 25. 25 times 1 is 25. You add those together, you get -75. -75 times 1 is -75. You add those together, you get 0. So it works again. Works every time. So 1 works. Stop and factor. X minus 1 will be a factor. The other factor will be your quotient, which is x to the third power minus 3x squared plus 25x minus 75, still equal to 0. And normally, not even normally, seems like most of the problems this isn't the case, but it is possible that if you still have x to the third power in your factor, that you'll have to do more synthetic division to break this down even further until you hit x squared. Once you have a quadratic factor, then you can get the rest of your factors without, sorry, I said rest of your factors. You can get the rest of your zeros or your roots without doing synthetic division. But you have to usually get it down to x squared first before that becomes possible. The only exception to that, which seems to be a common exception, is, and it's because of the way they have the answers set up that you're able to do this, we can actually factor this using factor by grouping. So let's try that out. So we'll group the first 2 terms together, group the second 2 terms together. And I can just tell you on this problem, factor by grouping will work. It seems to work every time. There could be 1 or 2 homework problems where if it's degree 4, you find a 0 that works, you factor it, your new factor is x to the third power, and factor by grouping may not work, and you have to do more synthetic division to break that down until you get x squared as a factor. Then you can get the rest of your zeros or your roots from that factor by other means besides synthetic division. But this problem, factor by grouping, always seems to work. So once you get it down to x to the third power, give that factor by grouping process a try. Factor out the common factor here, which is x squared. You'll have x minus 3 left over. The common factor here is 25. Factor that out, you have x minus 3 left over, and this is how you know factor by grouping is working. This has to be the same as this. And this is how you would know if it's not working. So if you try factor by grouping, and this parentheses does not match this parentheses, it's a dead end. Factor by grouping doesn't work. You'll have to go back and do synthetic division in order to break this down even further. But as long as these match each other, you're good to go. You factor out the x minus 3, that's a common factor here, and that leaves you with x squared plus 25 as your other factor. And then you can get the rest of your roots from these factors here. So x minus 3, set it equal to 0, solve for x, you get x equals 3. So that's another one that would have worked from our list of guesses that we had earlier. But these 2 roots you would not find on that list, right? We set x squared plus 25 equal to 0. You can't even factor it. So earlier when I said you can find the rest of your factors if it's quadratic, well, you might not even be able to factor it. Like in this case, there are no more factors to find because it can't be factored. But we can still get our zeros or our roots out of this factor because it's quadratic. We can either use the quadratic formula, or in this case, we can just solve it for x, right? Subtract 25 from both sides, you get x squared equals negative 25. Take the square root of both sides, you get x equals plus or minus 5i, which again, you would never find by the synthetic division process because that process only finds rational roots. It doesn't find imaginary roots. So the only way you're going to get to these roots is by factoring and getting it down to a quadratic factor that you could then solve, right? And so don't forget, so your final list of answers would be 3 plus or minus 5i, and remember we had 1 at the beginning. So those are all the roots to that equation. And remember the, what is it called? I can't remember the name of the theorem now, but the theorem that says the degree of the polynomial is the number of roots that you should have to the equation, right? This was a degree 4 polynomial. We have 4 roots to the equation, so we have found all of them. All right, let's take a look at the next example. Okay, so here we are looking to find the x-intercepts and describe the behavior of the graph of the polynomial function at the x-intercepts. This problem can be done very quickly. Again, you won't have quite these prompts on Canvas that you do on Math Excel / My Math Lab. So you'll have to kind of piece it together yourself without these kind of hints that these give you here. So you'll just be given this function, and you want to determine if the graph crosses or touches at the x-intercept. So find the x-intercepts, determine whether the graph crosses or touches. To find the x-intercept, we are going to set y equal to 0, right? And remember, f of x is the y variable, so we're setting that y equal to 0. So we get 0 equals x plus 9 to the third power times x minus 9. Now, what you don't want to do is multiply this out. You don't want to take x plus 9 times x plus 9 times x plus 9 and FOIL that out. That's a bad idea. It's already factored. That's very helpful here. So all you have to do, since it's already factored for us, we already have the factors, is set each factor equal to 0 to find the roots of this equation. And those will be our x-intercepts. Right, so solve this for x, you get x is equal to negative 9. Solve this one for x by adding 9 to both sides, you get x is equal to positive 9. Right here, we're subtracting 9 from both sides. So here are the x-intercepts. They both pair with y equals 0. And so we have, as our x-intercepts, I'm going to write it over here, I guess, we have negative 9, 0, and we have positive 9, 0. Right? So those are your x-intercepts. That's what would go into this blank space here. But then you want to know, does the graph cross or touch the x-axis at these points? And the way you're supposed to determine that is by looking at the multiplicity. And the multiplicity is determined by the exponents, just like we saw earlier. So for this x-intercept, negative 9, the multiplicity of that root was 3, which is an odd number. If it's odd, the graph will cross the x-axis at that point. Okay, sorry about that. I guess we'll just do it like that. For this root, the multiplicity is 4, right? The exponent that gave us that root was 4. So the multiplicity of this root is 4. And that is an even number, right? And so if it's an even root, sorry, not if it's an even root, if it's an even multiplicity for that root, the graph will touch the x-axis but not cross. So it'll cross at negative 9, 0. It will touch at positive 9, 0. Let's look at this next problem here, number 11. So this one is another quick one. This one was pretty quick, even though there was a lot of details to look at. This one wants to know, use the leading coefficient test, this is for in behavior, to determine whether y approaches infinity or negative infinity as x approaches infinity. So we're only looking in one direction here for this in behavior. X approaches infinity, that direction is to the right. So remember x, the x variable, the x-axis runs left to right. Positive infinity would be to the right. So x approaching infinity means as the graph goes to the right. What we want to know is, what is the graph doing? Is it going up or is it going down? So y is the axis that goes up or down. Positive infinity would be the up direction. Negative infinity would be the down direction for y. So that's the question, is does it go up or down as the graph goes to the right? So that's how you want to translate this question. Now here, the degree is 9. So to answer this question, you have to look at the degree. Well, I kind of spelled that funny, but the degree is 9. And what matters about that is the degree is odd. And the leading coefficient is the other thing you need to look at, which is negative 10, right? So I don't know how I want to, being kind of lazy here, I don't want to have to write it all out, but the leading coefficient is negative 10. What matters about that is it's negative. All right. And so if the degree is odd and the leading coefficient is negative, what is the in behavior as the graph goes to the right? What I think of for this scenario, when the degree is odd, I think of this graph here. This is the graph of y equals x to the third power. So that's what comes to mind. As soon as I see the degree is odd, this is the graph that comes to mind. And even though that's not the equation I'm working with, it fits in the same category of in behavior, right? If the degree is odd, all of them that have an odd degree belong in the same category. Now here the leading coefficient's negative, whereas here it's positive. So if I wanted to change that, negative x to the third power, putting that negative sign there is just going to flip the graph over. So now it looks like this. And even though this equation looks nothing like the one I was given in the problem, they have the same end behavior because they belong to the same group. They have the same characteristics. Any polynomial with an odd degree and a negative leading coefficient will all have the same end behavior. So this one will have the same end behavior as this one. But this is one I can easily remember. It goes up to the left and down to the right. All right, so this is going to go down to the right. And that's the one I'm interested in, right? I want to know what's the graph doing when it goes to the right. I just found out it's going to go down. Now that means y is going to negative infinity. So what you want to put into the blank space here is negative infinity. As the graph goes to the right, it's going to go down. I don't know, there seems like there's a better way to word that, but as the graph heads to the right, it decreases. It's going down to the right. Okay. Number 12. All right, so we want to sketch the graph here. A lot of students will kind of skip on the details for this, but we talked about in section 3.4 the 4 things you want to find to help with graphing these functions. That is symmetry, the y-intercept, the x-intercepts, and the end behavior. Now you can really kind of skip the first two. I don't know if you really skip the second one, but the first one, the symmetry one, you probably could do without. This one we can use the shortcut. The exponents are mixed, right? We have one odd power, one even power, and so it's neither, right? In order for a polynomial to be an even function, all the exponents have to be even when it's multiplied out like this. To be an odd function, all the exponents have to be odd. If it's mixed up, it's neither, right? So this function's neither even nor odd, which means there's no symmetry. There's no, and again, I hesitate to make such a broad conclusion about this function. Maybe there is some kind of symmetry to it, but it's not one of the basic symmetries that we talked about in chapter 2. All right, so symmetry is not going to help us out. What about the y-intercept? We'll plug in 0 for x. That's how you find the y-intercept. We'll get 0 to the third power plus 4 times 0 squared. That's going to be 0 plus 0, which just gives me 0. And so the y-intercept is at 0, 0. And so that gives me this point here. The x-intercepts are more interesting, right? You plug in 0 for y, so you're going to get 0 equals x to the third power plus 4x squared. And then you want to solve this polynomial function. You do that by factoring. So thankfully we don't have to do p's and q's. We don't have to do synthetic division. This is factorable. You set each factor equal to 0. You get x equals 0 and x plus 4 equals 0, which gives me x equals negative 4. And so you get these 2 points, right? You get 0, 0 again, right? You had that for the y-intercept. Well, that's also an x-intercept. So you get 0, 0, but you also get negative 4, 0. Not only do you get these points, so you have also negative 4, 0, which is right here, but you also know the behavior of the graph at those points. You know whether it's going to cross the x-axis or bounce off the x-axis by looking at the multiplicity, right? So here, x equals 0 has a multiplicity of 2, which is even, which tells me that this graph will touch the x-axis at that point. Here, this exponent is 1, so this root has a multiplicity of 1. That's an odd number, which tells me that this graph will cross the x-axis at this point. So keep that in mind. The last thing that we want to find here is the end behavior, which is just like what we talked about for the previous problem. And I'm looking for a good space to put this at, and I don't really see one. So I guess over here, we can still see the function right here, so that we should still be able to figure this out, is based on the degree of the polynomial, which is 3, and the leading coefficient, which is a 1. So that's an odd degree, positive leading coefficient. So it's just like the problem we just looked at. This is the graph you should think of for odd degree. Positive leading coefficient, this one is also a positive leading coefficient. So this is my end behavior. It's not what my graph looks like exactly, but the end behavior will be the same. It's going to go up to the right, and down to the left. And I don't need to put this in terms of x going to negative infinity and y going to negative infinity, which is what happens here, right? Y goes to negative infinity as x goes to negative infinity. I don't need to word it in that way. It goes up to the right, down to the left. This is perfectly adequate for describing the end behavior to help us figure out what the graph should look like. All right, so let's go back to this graph. It's going to go down to the left. So after you get past all these points, it ends up going down to the left and it goes up to the right. So starting from down here, we'll reach this point where the graph will cross the x-axis. So it's going to cross above a certain ways. We don't know exactly how far, or I can imagine probably around -2 is where we're going to hit the turning point and head back down to this. I'm doing a horrible job of drawing this. Let me try that again. All right. It looked okay up to this point. I guess maybe not. Okay, let's just start from here. I'm still doing a bad job. All right, passes through that point, hits -2, but how high up do I go? You would need calculus really to determine that. Or you could just take -2 and plug it in. But how do you know -2 is the maximum point right here? It might not be. Calculus would be the way to answer that question. But we are not going to use calculus. So I'm going to go head up a certain ways, then head back down towards the next x-intercept, which is at 0, 0, where the graph will touch the x-axis. So it's going to bounce off of that and then head back up. And then it lines up with this end behavior of going up to the right. And so that is what the graph looks like. It's a good sketch. It's a good idea of what the graph looks like. This one, you just want to find the domain. And the shortcut for doing that is to take the denominator and set it equal to 0. Because you want to find out what numbers would make you divide by 0, and then remove those numbers from your domain. So start off with the assumption that the domain is all real numbers. Find out what would make you divide by 0, and pluck those numbers out. Whatever's left is your domain, right? So when is this going to equal 0? Well, it's hard to tell just by looking at it. Now in the past, we've had easier ones where you can just look, like this one, right? Number 14, right? I can see this one, -3 is a bad number, right? I don't have to solve it. I don't have to do any work. I can just tell if I plug in -3, that's what would make this equal 0. And so that would be the number you'd want to pluck out. But this one's more complicated, so we actually need to do some work to figure this one out. So let's do that work over here. Take the denominator and set it equal to 0, and then solve for x. And this is going to tell me what x is not allowed to equal, right? This is what's not allowed to occur. The denominator is not allowed to equal 0. So when I solve this for x, it'll tell me what x is not allowed to equal. I take those numbers out. Whatever's left is my domain. Now to solve this equation, it's quadratic. We can solve it by factoring. Two numbers that multiply to -24, add to +2, will be +6 and -4. Set each factor equal to 0 and solve for x. I'm just going to kind of skip those details. You get x equals -6, x equals +4. That's what x is not allowed to equal. X is not allowed to be -6. X is not allowed to be 4. And so we want to remove those numbers. So my domain is every number but -6 and 4. But we want to write that in interval notation. We can't just, if we could describe it in words, that would be perfect. The domain is any number but the number -6 and 4. But as an interval, it's a little bit more difficult to describe. Right? So here are the numbers we want to skip. 0 is okay, but we want to skip -6, we want to skip 4. So put open circles above those numbers, and then shade everything else in. Everything to the left, everything to the right, and everything in between. That's your domain. So let's describe these shaded regions as intervals. This is going to go from -infinity to -6, where there's a break, so I have to take a pause there. Then from -6 to +4, where there's another break. And then from +4 to infinity. And I really kind of messed myself up here because I didn't leave room for the union symbol that you would need to put here. So union, union, and there's the domain. So here's the domain of that function. These are all the numbers you're allowed to plug into that function. All right, so that's number 13. We only have 2 more problems left, so we're pretty close to being done. Number 14, determine the equation of the asymptotes. Remember, there are 2 types of asymptotes. There are vertical asymptotes, and there are horizontal or oblique asymptotes. Horizontal or oblique asymptotes, there's only one of these, right? It'll either be horizontal or oblique. Right? So to find the vertical asymptote, it's just like finding the domain. You take the denominator, you set it equal to 0 to find out what x is not allowed to equal. Whatever x is not allowed to equal, that will be a vertical asymptote. So for this problem, the vertical asymptotes would have been -6 and 4. Those are the numbers x is not allowed to equal. I think the grammar was wrong on that. Those are the numbers x is not allowed to equal. I guess that makes sense. And so those would be your vertical asymptotes. For this one, you subtract 3 from both sides, you get x is equal to -3. This is what x is not allowed to equal, so that will be the vertical asymptote. X equals -3 is the vertical asymptote. To get the horizontal or oblique asymptote, there are shortcuts you can use, but not on this problem. This is the one where you can't use a shortcut. The only way to find this asymptote is to take the denominator, which is x plus 3, and divide it into the numerator, which is -x squared plus 2x. All right, so what do I multiply to x to get -x squared? I multiply by -x. -x times x is -x squared. -x times 3 is -3x. Then you subtract, so these will both change sign. The highest power of x cancels out. You combine these together, you get 5x. You bring the next term down, but there isn't one, so we just leave it blank. Repeat the process. What do you multiply to 5 to get 5x? You multiply by 5. Now there's more to do to finish the division, but there's not any more to do to identify the asymptote. The asymptote is the quotient here. So if I want to see what the remainder is, yes, there's some more work to do. But for the asymptote, you don't really care about the remainder. The asymptote is the quotient. It's y equals this quotient here. So the asymptote is y equals -x plus 5. And it's an oblique asymptote. There is not a horizontal one in this case. It's just oblique. So that would be the oblique asymptote. All right, we have one more example left to go. Okay, last problem. Find all asymptotes, x-intercepts, and y-intercepts for the graph of the rational function and sketch the graph of the function. So just like the last problem, to find the vertical asymptotes, you take the denominator, you set it equal to 0, solve for x by adding 2 to both sides, and you get x is equal to 2. And that's it. So that is the vertical asymptote. There's only one. Now I will say there are alternate versions of this problem where you might get 2 vertical asymptotes. So they don't all work out exactly like this. They're all of them are this type of problem, but some of them will give you 2 vertical asymptotes instead of just 1. And to get that, you'll have to factor this and solve it to find the 2 vertical asymptotes. For the horizontal asymptote, it is not oblique this time, it's horizontal. Here the degrees are the same, so the shortcut is to take a ratio of the leading coefficients. So the leading coefficient on top is 2, the leading coefficient on the bottom is 1. 2 divided by 1 gives me 2. And so the horizontal asymptote is y equals 2. That's a shortcut you can use when the degrees are exactly the same. The degree on top is 1, the degree on the bottom is 1. And so you can just take a ratio of those leading coefficients. If the degree on top is smaller than the degree on the bottom, then the asymptote is just y equals 0. That's the other shortcut that didn't come up in this review. All right, the x-intercepts. So we're going to find the x-intercepts. We'll do that here. You set y equal to 0. So remember, this is the y variable here. We're setting that equal to 0. So we get 0 equals 2x plus 3 over x minus 2. And remember, we talked about this in 3.5. When you have a fraction equal to 0, the denominator does nothing. It's just the numerator that will make that happen, right? So the only way you can get a fraction to equal 0 is to get the top of the fraction to equal 0. So we just focus on that. So when does 2x plus 3 equal 0? Let's solve it for x and find out. Minus 3 from both sides, divide by 2, and you get that x is equal to -3/2. That's your x-intercept. It'll be -3/2, comma 0. Right, and so that would be the x-intercept here. Sometimes there are no x-intercepts. So if, for example, your fraction is like 1 over x minus 2 or something, when you set that equal to 0, there's no solution. And so that case, there would be no x-intercepts at all. Y-intercept, right? That's the last thing we want to find. So let's go and find the y-intercept. For the y-intercept, we're going to set x equal to 0. So we'll have f of 0 equals 2 times 0 plus 3. I hate the way I draw my 3's on here. Over 0 minus 2, was it? Yeah, minus 2. Okay. 0 minus 2. These just go away, right? When you plug in 0, those just equal 0. They just disappear. And you end up with negative 3 halves. And so my y-intercept is 0, comma, negative 3 halves. So that'd be the y-intercept. All right. And so that would be the answer here. First, we want to draw the vertical asymptote, which was at 2. All right, it's this vertical line at x equals 2. This is kind of weird because like that was the vertical asymptote. Well, the horizontal asymptote was also 2. That's kind of confusing, right? But it's y equals 2. So it's this horizontal line right here. We have these points, 0, comma, negative 3 halves. That's going to be halfway between negative 1 and negative 2. And negative 3 halves, comma, 0, which again is kind of confusing because you keep getting the same thing. And the reason I know it's between negative 1 and negative 2 is I'm thinking of it as a decimal, right? This is going to be negative 1.5. That's what helps me know where to put that point. So the graph to the left of this vertical asymptote is pretty well defined for us here. It's going to pass through these 2 points and then approach the asymptotes without crossing or touching. But what is the graph doing on the right-hand side? Well, pretty good guess that it's going to be up here, but let's confirm that by plotting a point on the right-hand side. So pick a number that's to the right of x equals 2. So I'll pick x equals 3, all right, something bigger than 2. Plug that into the function. So we'll have f of 3 equals 2 times 3 plus 3 over 3 minus 2. That's going to give me 6 plus 3 over 1, which is going to give me 9. Sorry, I guess I was writing a little too fast. So you get 3 comma 9. I guess I could have put it over here, which I didn't really leave myself enough room for 9. It's going to be pretty high up here, right? But that makes it pretty clear that it's going to be above the horizontal asymptote. And who knows how low it's going to swoop down here, but then it's going to eventually approach the horizontal asymptote without crossing or touching. And same thing here, right? This is going to keep getting closer to the vertical asymptote without crossing or touching. So this is what the graph looks like. This is how you might draw it out by hand. It's not the best drawing, but it'll do. Anyways, that concludes the video on the review for the Chapter 3 exam. Thank you for watching. I'll see you in the next video for Section 4.1.